Okay, so for today, we will be discussing finite groups, and I am teacher Joseph, and I will teach you everything you need to know about finite groups. So let's first look at the definition. Definition 1.4 about order, finite group, infinite group. So let G be a group, and the number of distinct elements in G is called the order of G, and is denoted by this, which is the order of G. It is read as the order of G. Now, if the order of G is finite, we say that G is a finite group. Now, if the order of G is equal to the positive infinity, then G is called an infinite group, or a group of infinite order. So we have two groups. We have two possible groups, finite groups and infinite groups. So let's look at that. So here, in the right, we have our infinite groups. We can say that this is a group, and this is the amount, each person in the world. So let's say each person in the world is lined up. So this is the first person, second person, third person, fourth person, fifth person. So we can label it as that. But then we won't really know what's the end, since we know that every person can die and another person can be born again. So this can be the 1 millionth person, 1 million 1th person, and you will never really end. So now, to make that into a finite group, we have here this group. So this group is what we would say the presidents, the previous presidents, or presidents in the Philippines. So we have here Ferdinand Marcos, we have Pinoy Aquino, we have Rodrigo Duterte, Ferdinand Marcos, Emilio Aguinaldo. So it's basically a group, and it's basically all the presidents of the Philippines. So now let's look at that in a food perspective. So here, we're trying to count all the fruits in the world. So let's say this is all the fruits in the world. So we know that we can count 3 bananas, 4 bananas, 5 bananas, and then 2 blueberries, which is like fruits. We can count it as fruits, and then it won't really end. But to make it into a somewhat finite group, we can use the group of the types of fruits. So let's say coconut, kiwi, avocado, orange, or apples. So we can label our groups. The elements of our groups is basically the type of fruit. So it's the coconut, kiwi. It's not how many they are, but it's what the fruit is. Okay, so now let's look at that. Then let's have an example. So let's say we have a finite group of G. So G is a finite group. We can label it as, so we can have G is equal to the addition under modulo 8. So yes. So this is the addition under modulo 8. So this is what we call a finite group. Now, we know that addition under modulo 8, we can have the set 0, 1, 2, 3, 4, 5, 6, and then 7. So 8 modulo 8 is simply 0. That's simply the same thing. So now recall that our definition says it's the number of distinct elements. Now the order is the number of distinct elements. So to find the order of this group, we need to find distinct elements. So since 8 is under modulo 8, it will become 0. 8 is simply the same as 0. Now, if 8 is as simple as 0, then 8 will not be distinct. Now, these are our first distinct elements. Now, we just have to count this. So, this is 0, 1. So, 1, 2, 3, 4, 5, 6, 7, 8. So, to find the order of G, it is simply 8. We simply counted how many there are in the group. So, now, let's say this one. So G is equal to 1, negative 1, I, negative I, under multiplication. So to find the order of this group, we will simply count how many elements are there in this group. Oops, sorry. This is a bracket. So now we're simply gonna count the how many elements are in this group, how many distinct elements. So 1 is distinct, negative 1 is distinct, I is distinct, negative I is distinct. So 1, 2, 3, 4. So since there's 1, 2, 3, 4, the order of this group is simply 4. Now, let's try to find G is equal to U9. Oh, sorry, it's not a bracket, it's parentheses. U9 under multiplication modulo 9. So this is now a finite group. This is what we call a finite group. It's a finite group since the elements of this group are a set of numbers that are co-primes of 9. So the co-primes of 9 are simply 1, since it's basically the only factors of 9 and that number is 1. So here 1, 2, since 2 cannot divide 9, 2 is a co-prime. So how about 3? 3 can divide 9, which is a co-prime. Which is not a co-prime, rather. So how about 4? 4 does not have any common factors except 1. So it is a co-prime. Now 5, it does not have any factors. It does not have any common factors with 9. So it is a co-prime. 6, however, 6 has a common factor, which is 3. So the next one, which is 7, and then 8. And then 9 is divisible by 3, 9 is divisible by 9. So it's not a co-prime of 9. 9 is not a co-prime of itself. Okay. So here, to find the order of this, we're simply gonna count the distinct elements. So 1, 2, 3, 1, 2, 4, 5, 7, and 8. So 1, 2, 3, 4, 5, 6. So the order of this group is simply 6. Okay, so now let's try to I'm so sorry. So let's try to move on to the next. So let's say we have G is equal to the set of all real numbers. The set of all positive real numbers. So if we have this, all the positive real numbers, it's simply the set is simply 1, 2, 3, 4, 5, ... until 1 million, let's say 1 million, and you still won't end, and then ... So up until infinity. So it's infinity. So we're gonna count how many elements there are. Now, since it's an infinite set and it has infinite amount of distinct elements, so it will become, the order is simply positive infinity. Okay. So that's how we define an infinite group. But that is not the focus of our topic today. So now, let's move on to definition 1.5. Where a raised to n. So let G be a group and a is an element of G and n is an integer. Then a times a times a times a times a of n copies. That's basically it. If n is less than 0. If n is greater than 0. Now the identity element, you will get the identity element if n is equal to 0. Sorry, there should be an a n here. A of n is equal to that. So now a inverse is raised to negative n is basically equal to a inverse times a inverse times a inverse times a inverse times a inverse if n is greater, if n is less than 0. So now let's try to look at that. So let's have an example. So example, we have G is equal to addition modulo 5. Now, we want to have a as equal to 2. Now, we're going to find 2, 0, 2, 1, 2, 2, 2, 3. And then 2, 4, 2 inverse, and 2, 3 inverse. So, let's try to find that. Since the operation is addition, we know that the operation is addition, we're gonna try to find it. Now, let's have the first one. So, 2, 0. 2, 0, as we can see, if we will get the identity element if n is equal to 0. So, here we have a raised to n, right? So, our a is 2. Now, 2, 0 will simply get the identity element. Okay, so now let's try to define that better. So 2, 0, which means we won't be adding any zeros. And what is the identity element of? What's the identity element of 2 of addition modulo 5, which is also equal to 0? The identity element is 0, because if you map the identity element to itself, you will still get the identity element. So if you map 0, 0 plus 0, you will simply get 0. Now, okay. Now, let's have b. b is 2 raised to 1. So, to get 2 raised to 1, it is not... So, okay. So, to get 2 raised to 1, it will simply mean we will get... And our n is 1. 1 is greater than 0. So, if 1 is greater than 0, we will use this. A times A times A, n copies. So if we have n copies, we have 1 copy, you'll simply get 2. So your answer is 2, to get 2 raised to 1. Now, we will try to find the next one. So 2. 2 raised to 2. So 2 raised to 2, our n now is still 2. So 2 is still greater than 0. So if 2 is greater than 0, we will use this again. Now we have n copies. So if we have n copies, we will simply use 2 plus 2. So bakit plus 2? So y plus 2, we will be using addition. Our operation for this group is operation. So we will simply do 2 plus 2, which is equal to 4. Okay, now let's try to find the next one. So d. Our d is basically 2 raised to 3. Now we're trying to find n copies. 2 plus 2, since our 2 plus 2 plus 2. So we have 3 copies, right? So 2, 2, and then 2. 2 plus 2 plus 2. We have 3 copies, and then we're adding it since our operation is addition. So 2 plus 2 plus 2 plus 2. So 3 times, it is simply 6. Usually, we know that 2 raised to 3 is equal to 8. But since we're not under multiplication and we are under addition, we will be using 2 plus 2 plus 2 because we are under addition. Okay, now, for 2 raised to 4, again, we will do n copies. So we're going to be 2 plus 2 plus 2 plus 2. That's where we will get 8. But in normal algebra, we know that 2 raised to 4 is equal to 16. But we are not doing normal algebra. Okay, so now, we're trying to find the inverse. So try to find the inverse. 2 inverse. Okay, so now, we're gonna try to find the element which we will... Our answer for 2 inverse is basically if we have 2 raised to 1 plus 2 inverse, we will simply get the identity element, which is 0. So now to find that, let's say 2 inverse is equal to... So we have our 2 raised to 1 here. 2 raised to 1 is equal to 2. Now, we're trying to find 2 inverse. We're trying to find 2 inverse, which is equal to 0. Now, to try to find that, we will simply get 2 inverse. We will simply get 2 inverse equals to 0 minus 2. But we don't have a negative 2 in our elements. Now, what can we try to if we try to do that, if we try to do it with simple algebra, we won't arrive with the answer. So now, what can we try? What can we try with 2 plus 2 inverse to get 0? We can simply try to use this. So we can substitute 2 inverse with 4, right? If we substitute 2 inverse with 4, we will get 0 because 2 plus 4 is equal to 6, and 6 modulo 6 is simply 0. So that's how you get the inverse. So now our answer, 2 inverse, is equal to 4. Okay, so I'm sorry, this is, instead of 8, this is 4. Instead of 6, this is 0. No, sorry, this is 2 because modulo, right? Okay, so now we have 2 inverse 3. Let's try to have that 2 inverse 3. So we know that 2 inverse 3 is 4. We can try to make this as 2 inverse 1, and then outside is 3. And we know that 2 inverse 1 is 4. So now we're gonna map that to 3. Now we need to have 3 copies of 4. So 2 inverse 3 is also equal to 4 plus 4 plus 4. Again, we're using addition because addition is our operation. Now there is 4 3's because we're trying to find n copies, 3 copies. So now 2 inverse 3 is equal to 12. But 12 modulo 6 is equal to 0. So we know that our 2 inverse 3 is still simply an identity element, which is 0. So that's all you would need to know, how to try to find the order and the finite groups, right? So that's all you need to know in finding the finite groups and its